Alright, for this problem what we want is we want an energy diagram for position A, position B, position C, and then we'll go with the D where the spring is compressed. So at position A, what we want to think about is, well, what's the object doing? We're going to say released from rest. Maybe I better write that up here. And since we have a vertical, so we have a change in height, that implies we have gravitational potential energy. That should be included in our system. Between B and C, we have a rough surface. So that implies we want to use dissipated energy. We could call it dissipated energy, or we could say work done by friction. Since we haven't talked about work yet, I'm going to use the dissipated energy. And then we have a spring in the system. That implies we want to include elastic potential energy. Let's see, let's put this A down here. First I was going through the summary of what we needed to include in the system. So anytime you look at a diagram of a problem, or you read through a problem, and it lists any of these things, this is what you want to think about. Changes in heights, go with potential energy. Rough surfaces, you want to think of friction, work done by it, or dissipated energy. And if there's a spring involved, think of elastic potential energy. Alright, then we're ready to break it down by part. For part A, just create a circle, and if the object is at rest initially at the top, it's not going to have any kinetic energy, it hasn't traveled across the surface yet, and it hasn't touched the spring yet. So all of the energy has to be stored gravitationally. At B, we have moved across a surface, but the rough surface, as indicated by the little waves, isn't encountered until it's between B and C. So at B, which is right before that rough area, all of the energy then is stored as kinetic. Because we're no longer at our elevated height, we're at the lowest position on the diagram. So any potential gravitational potential energy we had is stored in some other way, and that other way now is movement. So then by the time we get to C, we haven't, circle size should stay the same because we're not going to lose energy anywhere. We're going to account for it everywhere. Now we've moved across the rough surface. Meaning friction has done some work on the object, or we've moved some of the energy from the kinetic category to a thermal category. Generally, when we talk about dissipated energy, it usually goes with heating up a surface, so it's a thermal energy. The way to think about that is if you rub your hands together, there's going to be friction between your hands, so the work is going to be done by friction. And notice the result of that work is the increase in surface temperature of your hands. And so that we're still moving. So the other thing we have at C is kinetic energy. And then at D, we have the spring completely compressed. We're not moving. We're on the ground. And so we have dissipated still. And then the rest is elastic. Now the little thing to note down here, so let's put this in red, and we don't need it quite that big. There we go. Note. Once you place dissipated energy, you can't get it back. That's one reason we call it dissipated. So we'll write that as once E dissipated is used or dissipated energy is used, it can't be transferred back to any other type. We'll say any other storage mechanism. You can think of that as it's the energy category that once you put it in, it doesn't come back. It's there, but you can't do anything useful with it. Alright, so that takes care of that example.